Welcome to this session on combinational circuit design. Today, we will explore the systematic approach to designing these circuits. This is essential in digital logic and design. Let's take a look at the overview of our design process. It consists of 4 key steps, starting with problem analysis. Then we'll move to the construction of a truth table. The third step involves deriving a Boolean expression, and finally, we'll focus on circuit implementation. Step 1. Problem analysis. This crucial initial step involves understanding what we aim to achieve with our circuit. Some key questions to ask include: what are the input variables? What are the output variables? What specific functionality are we trying to achieve? And are there any constraints we need to consider? For example, in a 3-bit majority voter, the inputs are A, B, and C represented as 3 bits, the output is M represented by a single bit, and the function is to output a 1 when a majority of the inputs are 1. Step 2. Truth table construction. Continuing with our 3-bit majority voter example, here's how we construct the truth table. The table lists all possible combinations of inputs, A, B, and C, alongside the corresponding output M. For example, if A, B, and C are 0, 0, 0 respectively, the output M is 0. If the inputs are 0, 1, 1, the output M is 1. The construction steps include listing all possible input combinations. For n inputs, create 2 to the power of n rows. Determine the output for each combination. Verify the logic requirements. Step 3. Boolean Expression Derivation. Now let's derive the Boolean expression from our truth table, using the sum of minterms method, also known as SOP. Looking at the rows with an output of 1 from the truth table, we identify the input combinations as 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. The Boolean expression is M equals a bar BC plus AB bar C plus ABC bar plus ABC. Simplifying this expression using Boolean algebra, we get M equals AB plus AC plus BC. Some simplification methods include algebraic manipulation, Karnaugh Maps, also known as K-maps, the Quine-McCluskey method, and Boolean algebra laws. Let's simplify our Boolean expression using a Karnaugh map, or K-map. This is a 3-variable K-map. From this, the groups identified are Group 1 AB, Group 2 AC, and Group 3 BC. So the final expression becomes M equals AB plus AC plus BC. Step 4. Circuit implementation. Based on our simplified Boolean expression, M equals AB plus AC plus BC, we can now implement the logic circuit. Here is the circuit diagram. Implementation steps include drawing in gates for each product term, connecting inputs to the appropriate gates, using an OR gate to combine the outputs, verifying the circuit functionality, and testing it with all input combinations. In summary, some key takeaways include: a systematic approach ensures reliability, truth tables capture all requirements, simplification reduces complexity, and verification prevents errors. For best practices, start with a clear problem definition, use K-maps for simplification, test all input combinations, and document design decisions. Following the 4-step methodology ensures successful combinational circuit design. These steps are: analyze requirements, construct truth tables, derive simplified expressions, and implement verified circuits. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.